Hey everyone, welcome back to Code Tales with her channel. Today's topic is binary search. We'll provide an end-to-end, detailed, and beginner-friendly explanation of this powerful search algorithm. Let's start by defining what binary search is. As you know, binary search is a searching algorithm used to find an element in a sorted array. Searching means finding a specific element in a list or collection. It's the process of deciding whether a search key is present in the data or not. Imagine you're searching for the word binary in a physical dictionary. You wouldn't start from page 1 and read every single word. That approach is called linear search, and it's painfully slow. Instead of checking every single word, you open the dictionary roughly to the letter you need. Instead, you open the dictionary in the middle. If the word you're looking for comes before the current page, you ignore the entire second half. If it comes after, you ignore the first half, as the dictionary is alphabetically sorted 1. This action immediately eliminates about half of the dictionary from your search, a core concept of binary search. By repeatedly cutting the search space in half, you find the word in just a few steps. This exact idea is called binary search, one of the most powerful and efficient algorithms in computer science. The golden rule of binary search is that your data must be sorted. This is an essential prerequisite for the algorithm to work efficiently. As you can see here, if the data is unsorted, binary search cannot be applied directly. It must be sorted first to function correctly. The second core concept is the divide and conquer approach, which gives binary search its power, leading to an O log n time complexity. Binary search works on the principle of divide and conquer. At every step, it eliminates half of the remaining elements. As its name itself suggests that binary, it just makes the array into two halves and search accordingly. Divide and conquer is about repeatedly breaking down a huge problem into smaller, manageable subproblems until they are simple enough to solve directly. Now let's explore the algorithm step by step to see how it actually works. Let's break down the standard binary search approach. Imagine an array of elements. We use pointers L for the left boundary, R for the right boundary, and M for the midpoint. The 4 core steps are: initialize left and right. Few people use start and end, and few use left and right, and few uses low and high. Whatever the indication is, the logic is same. Find the midpoint M. Compare M with the target value. Adjust L or R, and repeat, shrinking the search space until the target is found or the boundaries cross. Next, we look at the 2 ways to write the code: iterative versus recursive implementations. Binary search can be implemented in 2 ways. Iterative approach uses a simple while loop, uses constant space. O1, faster and more memory efficient. This is the preferred method, especially in interviews. Recursive approach. Function calls itself on smaller subarrays. Uses O log n space due to recursion stack. Code may look cleaner, but uses more memory. In interviews, recursion can be risky if you're not careful. Here is an example showing how the array is continuously divided based on whether the target is less than or greater than the mid value. For mid, we will consider floor value. Suppose if get mid value is 6.5, we consider it as 6. Let me explain the concept here. Suppose our target element is 4. Our mid value is 6. So 4 is less than 6. So we need to check the first half of the array. So indicate start to start, which is 1. And update the end or high to mid 1, which is index 4. Let's check mid over the updated low and endpoints. Now mid is 3, containing value 3. 3 is less than 4. So we need to check in the second half of the array. Like this, we need to check and ignore the half portion as the array is sorted. This is what divide and conquer approach is. We initialize low and high pointers. The mid is calculated. If the target is smaller, we search the left half. If larger, we search the right half by adjusting low or high. We have the array 1 to 11. So first we need to initialize the start and end points of the array. Here, start is 1 and end is 11. So now we need to find the mid element of the array, which is nothing but low plus high by 2. Here, low is 0 and high is 10 as we start the index from value 0. And the mid is 10 halves, means 5. SO index 5 is our midpoint. Now, we need to check our target value with midpoint. Suppose our target value is 6 and midpoint value is 6 means we are done. The element is found, and we'll return the index. Otherwise, we will check the target is less or greater than the mid. We will check left if the target is less than mid. And we will check right if the target is greater than mid. We update the low and high points accordingly for the second comparison. And will the steps, like finding the mid, checking the target over it. Repeat this until we find the element. If element is not found, means we will return -1. You can practice this binary search in any of the online platforms, like InterviewBit, LeetCode, etc. In LeetCode, it was 704.binary search. This C++ code demonstrates the iterative implementation of binary search, defining low, high, and mid, and adjusting boundaries within a while loop. Let's revise what we learned till now about binary search. Binary search is to find a number in a sorted array. It repeatedly divides the array into two halves and compares the middle element with the key. If the key is greater, it searches the right half. If smaller, the left half. This continues until the element is found or the search range becomes empty. Binary search has a time complexity of O log n. This means doubling the amount of data only adds one extra step to the amount of work the algorithm performs. In binary search, every step cuts the search space into half. First step, n elements. Second step, n by 2. Third step, n by 4. Fourth step, n by 8, and so on. This keeps happening until only one element is left. Mathematically, n by 2, power k equals 1, which means k equals log n. So the number of steps, comparisons, grows as log n, not n. In the graph, x-axis is nothing but number of elements. N, y-axis is number of comparisons. The curve rises very slowly, showing that even if n becomes very large, the number of steps increases only a little. Comparing linear search and binary search. To understand how fast binary search is, searching 1 million elements takes only about 20 steps. Searching 1 billion elements takes just 30 steps. That's insanely efficient. Binary search is widely used in competitive programming and interview settings due to its efficiency and foundational nature. Be aware of common pitfalls. First, infinite loops due to incorrect pointer updates. Using low equals mid or high equals mid instead of mid plus 1 or mid minus 1 can cause infinite loops. Second, wrong loop condition. For standard binary search, always use while low less than equals high. Second, ensuring the data is sorted before applying the binary search. And third one is handling edge cases like empty arrays or targets outside the range. Always check if the array is empty before starting. As an interview tip, practice both the iterative and recursive solutions. Also, be prepared to adapt the logic for variations, such as searching in a rotated sorted array. Low plus high by 2 formula works for small arrays. So, what's the problem? The problem happens when numbers become very big. Computers can only store numbers up to a limit. That sum can become too big for the computer to store. This causes overflow, which means the value becomes wrong. You don't see this with small examples, but real programs and interviews care about this. Instead of adding first, we subtract first. The formula is mid equals low plus high minus low by 2. High minus low is never big, so the computer stays safe. No overflow risk. Thank you for watching this video. Do subscribe to the Code Tales with Her channel for more such content. Like, share, subscribe, and comment.